Hello and welcome back. Today we're going to be talking about Diels-Alder reaction basics. This means that today we're going to be focusing on the Diels-Alder cycloaddition reaction, of which the archetypical reaction is shown here. It's a 4+2 concerted cycloaddition, meaning we're still within the realms of pericyclic reactions, and it occurs between a conjugated diene and an alkene, which is typically called the dienophile. Given that this is a pericyclic reaction and all the bonds are going to be breaking and forming in a single step, ensuring you maximise orbital overlap between the two reactants is what guides reactivity in these reactions. So Diels-Alder reactions are thermally allowed by the Woodward-Hoffmann rules, and being a 4+2 cycloaddition, we need to consider the 4p orbital arrangement of the diene and the 2p orbital arrangement of the alkene. Like virtually all chemical reactions, one of our reactants will be in the HOMO configuration of orbitals, and it will be reacting with another reagent, which is in the higher energy LUMO arrangement of orbitals. And given this orbital arrangement is so important for reactivity in Diels-Alder reactions, we need to know what these orbital arrangements look like. On the left, we're dealing with the diene. There are 4 arrangements of orbitals. Each of these states can hold 2 electrons apiece. And with 4p orbitals, that means there's 4 electrons we can place in these energy states, 2 in the bottom at psi1 and 2 above it in the psi2 state. This gives us 2 pairs of orbitals, each having the opposite orientation to the other. This gives us our double bond configuration, which we can see in our diene's structure. Now, if our diene absorbs energy in our thermal reaction to promote the electrons into the lowest unoccupied molecular orbital, that configuration is going to change. What we'll see is the center 2 orbitals will be in the proper orientation to form a double bond like so, and the outer 2 most orbitals will have the flipped orientation. Jumping across to take a look at the dienophile, it's a bit simpler considering we're dealing with only 2p orbitals. There are only 2 energy levels here, meaning at most we can fit 4 electrons. We have 2 electrons, so they're going to adopt this lowest state here. So our alkene will simply have a double bond. If our alkene or dienophile absorbs energy in our thermal reaction, the electrons will be promoted up into this LUMO band shown here. And in that case, our 2p orbitals will have opposing orientation, as shown. So to summarise, in our Diels-Alder reaction, we're going to be reacting a diene and an alkene. One of these species will be in the HOMO state, the other one will be in the LUMO state. Because Diels-Alder reactions are all about getting proper overlap of orbitals between our 2 reagents, we need to know what these HOMO and LUMO arrangements of orbitals look like. Now we've covered that, there's 3 ideas that we're going to talk about today that are relevant to Diels-Alder reactions. First one we're going to cover is the Alder endo rule. And to do that, let's imagine a scenario. We have 2 equivalents of cyclopentadiene, shown here in the center. Cyclopentadiene can act as a diene, highlighted in green here, but it can also act as an alkene by only considering one of the alkenes, as highlighted here in blue. There are 2 ways that cyclopentadiene can dimerize to form a dicyclopentadiene. They can overlap in such a way to form the exo product, shown on the left, which is the lower in energy of the 2 products, i.e. the thermodynamic product. The second way it could overlap, though, gives us the endo product, shown over here. It is higher in energy, but it forms much more quickly than the exo product. So if you perform this reaction, this endo product is what you exclusively see. It is the kinetic product of the reaction. He's showing you this situation diagrammatically. Here in the center, we have our 2 equivalents of cyclopentadiene. There are 2 reaction pathways it could go. It can either go to the left to give us our exo product, or it can go to the right to give us our endo product. The exo product, we can see that it winds up down here in this energy well, and it's lower than the endo product. So this is the thermodynamically favored product. However, given it's a thermally driven reaction, it's the transition state that's going to dictate which way the reaction is going to go. And we can see that this transition state for the endo product is lower in energy than for the exo product. So as you add energy, the reaction will proceed over this transition state to give us our endo product. which is still energetically favourable, but not quite as much as the exo product. So why would this be? Well, we need to understand why one transition state is lower in energy than the other. The first one we're going to consider is the exo product transition state. This is the one that does not form. Now, the reaction proceeds through overlap of these p orbitals. As drawn on the screen, the p orbitals are vertically oriented. So they basically appear up and down in the plane of the screen as you are looking at it. So for this reason, the two cyclopentadienes have to be flat and sit atop one another, kind of like stacking pancakes. For this exo transition state, we have good orbital overlap where the dashed lines are shown. Essentially, this overlap is perfect for the reaction to proceed, which is good, but certain p orbitals, the ones highlighted in red, are not undergoing any reaction at all, so they are not being stabilized. If we were to reorient the two cyclopentadiene molecules, it is possible to get stabilization occurring at these red p orbital locations. And we can see that for the endo product. So in the center, we're showing the endo product transition state. Once more, we've drawn our dashed lines where our bonds are going to be formed. However, if you look at the location of the two cyclopentadienes, they're now almost perfectly stacked on top of one another. So looking over here at the right, the orbitals highlighted in red, these are our primary orbital overlaps where our bonds are going to be forming. But if we look behind them, we can see that there are additional p orbitals that are also overlapping in the transition state. These are secondary stabilization interactions, and they lower the energy of adopting this transition state. So essentially, in both transition states, the red orbitals are present. Those are the primary stabilizing interactions that lead to the reaction proceeding. But only in the endo product do we get this excellent overlap involving all of the p orbitals, which stabilize that transition state more than for the exo product. It's the presence or lack of these secondary stabilization interactions that dictate which way the reaction is going to go. Here's a good point to remind you that one of our reagents is going to be in the HOMO, highest occupied molecular orbital state. Our other one is going to be in the LUMO, lowest unoccupied molecular orbital state. And if we have a look at these orbital arrangements, we can see that we have two orbitals with the same orientation, giving us our double bond to double bond. But looking at the bottom one, we can see that this one's going to be in the psi3 energy level, shown here, where we have this central pair of correctly aligned orbitals and the outermost p orbitals are oppositely aligned. And indeed, we can see that here. We have the central two orbitals aligned together, and the outer two mosts are in the opposite alignment. And when we stack our two cyclopentadienes atop one another, we can see that we have the same coloured orbital lobes all lined up to match and interact and stabilise this configuration. So this first idea of the Alder endo rule is basically that you should maximize overlap between as many p orbitals as you can, and that is going to tell you what the preferred product of the Diels-Alder reaction is going to be, typically preferencing this endo product shown here. Before we move on, just a quick guide to show you how to visualize or go from the transition state across to the product. So in this current example, we have an endo product and an exo product forming. We have two different transition states, which are shown on the left. I've drawn in the primary stabilizing interactions. So this is the point where the bonds are going to form. First thing you would do is you would draw in these two new bonds. Now, to create these two new bonds, you need two pairs of electrons. They are sourced from the alkene. So one pair of electrons from the alkene becomes one of these bonds. The other pair of electron is sourced from the diene. You can take one electron from this double bond, one electron from this double bond, and form our second bond here, and the remaining single electrons within our double bonds reform to give us our double bond at this position. So we go from our transition state, we draw in our bonds, we lose a double bond here, we lose a double bond from our diene, but we shift our single remaining double bond here to this position. Once we've drawn that in on either side, all we have to do is we just rotate this molecule. The way I've drawn it, we're rotating counterclockwise. I've left in this bolded bonds here. I've left in the green and blue highlighting just so you can see where all of these things wind up after you rotate them. After you've done that rotation, it's basically just cleaning up the structure a little bit. I find if you draw in these hydrogens or whatever functional groups are in this position, it makes seeing the endo and exo conformation easier for the reader to see. So just to really cement what I've been saying, for a Diels-Alder reaction to proceed, the frontier orbitals, so this HOMO-LUMO interaction, needs to match. That matching or constructive overlap, it needs to be maximized, which includes any secondary interactions of orbitals away from where the bonds are forming, and that gives you your preferred transition state geometry. Here's another example, just looking at 1,3-butadiene instead of our cyclopentadiene. We've got our diene on the top, we have our alkene on the bottom. We can draw in our primary molecular orbital overlap in red. We can also show our secondary molecular orbital interaction, and we can see that the orientation of these orbitals are perfect between the HOMO and the LUMO to stabilize and promote the reaction. Another thing to note is that it does not matter whether the diene or the dienophile is in the HOMO or the LUMO state. As long as one is in one and the other is in the other, you are going to get this excellent alignment of molecular orbitals to allow the reaction to proceed. Okay, idea number 2, conformation and diene reactivity. Here we have our 1,3-butadiene once more. And if you have that floating around in solution, it is in a conformational equilibrium, meaning it is shifting between this open chain form and this cissoid form shown here. Your diene must have this cis or cissoid conformation if it is going to react by a Diels-Alder reaction. If your 1,3-diene is locked in this open form conformation, it cannot undergo reaction in a Diels-Alder reaction, at least not in the diene role. It could theoretically react as an alkane, but the diene must adopt this cissoid arrangement of double bonds. Conversely, if you have a diene and it is locked in this cissoid conformation, that reagent is going to be extremely good for Diels-Alder reactions. It is locked in the conformation that promotes reactivity. And indeed, we can take this idea a little bit further by considering steric considerations of our 1,3-diene species. Here we have our 1,3-butadiene, but we have a large, bulky tert-butyl group in the 2 position. As I mentioned before, this is in a conformational equilibrium, meaning it is swapping between this open form and this closed cissoid form over here. Now, because we've added this bulky functional group, we've created this steric clash when our butadiene is in its open chain form. That means it would prefer to be in this cissoid conformation because that eliminates this steric clash. So we push our conformational equilibrium over onto the side that preferences reaction in a Diels-Alder way. It is one way to use chemistry design to preference this kind of reaction. Now, conversely, now we have 2 bulky tert-butyl groups on our butadiene backbone. All of a sudden, we've flipped our reactivity. We do still have these small steric clashes in the open chain form, but if our butadiene adopts the cissoid conformation, all of a sudden we have a very strong steric clash between our 2 tert-butyl groups. Now our conformational equilibrium is going to favour the open chain form, and this form can't undergo a Diels-Alder reaction. So by playing around with the sterics of our diene, we can influence the reactivity of our reagent towards Diels-Alder reactions. The last idea to talk about is the cis principle involving either the dienophile or the diene. So here we have 2 dienophiles, and they are going to react with our diene. This is actually quite an interesting diene in that when this central diene reacts, the new double bond that is formed by the reaction is going to be situated in this position shown here. And that essentially creates an aromatic ring shown down here in our products, which is another way of stabilizing our Diels-Alder reaction. But anyway, going back to our dienophiles, here we can see we have a dienophile that has a trans configuration, and on the other side we have the same dienophile, but it's in the cis configuration. When we undergo our Diels-Alder reaction, the steric arrangement of the substituents on our dienophile are preserved. So in our product, we still have a trans arrangement shown here, and on the other side, we still have a cis arrangement shown over here. We can have a look at the same principle involving our diene. So here we have our diene highlighted in green. We have our two phenyl groups attached to the side. We've got this sort of trans configuration. So trans. When it reacts with our alkene, we can see that we get the endo product and our phenyl groups are in this cis conformational relationship relative to one another. This should make a lot of sense given what we've covered already. So we can draw in our primary interactions. It's an endo product, meaning we have to pancake our alkene and diene on top of one another as much as possible to get the secondary orbital interactions occurring. And because our alkene and diene are stacked atop one another like pancakes, our two phenyl groups are going to orient themselves away from the dienophile, giving the stereochemistry we see over here. The reaction can only proceed in this syn manner. You'll never see a bond forming below and above the position. The cis relationship is locked in. So that's the basics of the Diels-Alder reaction, but there is a lot more to cover, including partial asymmetric synthesis involving Diels-Alder reactions, Lewis acid catalyzed Diels-Alder reactions and their effect on asymmetric synthesis, orientation phenomena when you're using unsymmetrical dienes and dienophiles, and we haven't really talked about the electronic nature of the diene or the dienophile, including inverse electron demand systems, solvent effects, mechanistic quirks, etc. That's it, and thanks for watching.